Hello, everybody. Let us start our discussion today. Last time we discussed about four vectors and how it is few properties of the four vectors. Today we'll start by revising our idea of the four vector, and then we will go to a little more general things called tensors, and let's see where we can go from there today. So first, a little bit of review. So what did we call vectors? I'm not defining it again here. So it is like in 4 dimensions. So we are all dealing with 4 dimensions. Let me write shorthand 4D. It has in general 4 functions. In a given reference frame S. This we call the components of the vector S, vector in the reference frame S. So we adopted this notation for a 4 vector. We said we can write it as the following. This is just the collection of 4 components A. And remember that each of these A alpha can be function of the coordinates. So let me just write it this way. So it can be function of the coordinates. So that is how we defined, or not necessarily defined, that is how what we called a vector. So every point, these 4 components can has different values. We then defined very specific type of vectors. We call them basis vectors. The way we denoted the basic vectors are like E0. 0 is the 0th basis vector. Remember, this is a vector, and then we said that the 0th place will have 1, the other places has 0. And then we have 4 basis vectors in 4-dimensional system. And this we can write something like E alpha. Once I have the basis vectors, these bases are coordinate dependent. It depends on which coordinate system. Actually, they define the coordinate system. So again, for the time being, I am using coordinate system, frame, etc. All reference frame, all synonymously. And so once I have that, I can write my basis, my vector A as its components times the basis vector in that reference system. In different reference system or different coordinate system, the basis vector remains as it is. The vector remains as it is, the basis vector changes, and the components changes. And that change in this particular case I have denoted by the prime in the alpha. So that is what I meant. So this is again something for us to remember. So remember that E alphas are vectors, A alphas are components, they are not vectors. Okay. We also looked at the scalar product, or sometimes it's also called dot product. Scalar because it gives us a scalar once we do the product. This is a product between two vectors a and b. And to define this, we bring in this quantity g alpha beta, which I have not said what it is, but we introduced this thing where, if you remember, g alpha beta was can be written like this, where the diagonal elements, which is the elements which have where alpha is equals to beta, are all like 1 minus 1 minus 1 minus 1 for alpha equals to beta equals 0 1 2 3, and all the other elements are 0. And this gives you a dot b gives you a scalar. So a dot b, it's obviously that this is equals b dot a, may not be as obvious, but that is equals to b dot a. So this is a scalar. When I say scalar, I mean doesn't change on coordinate transformation. We also talked about what are the types of coordinate transformation possible. In these lectures, we are mostly thinking of space-time type of transformation, which are for special relativity or Lorentz transformations. And that is what when I say that coordinate transformation, in the back of my mind, that is what I have. Now, the dot products are generating numbers from two vectors. So dot products are two vectors you are putting inside, and then it is giving you back a scalar number. Keep this in mind because this is something that we will be using later, this understanding. The dot product I can write in a little different way. So A, remember, I could have written on its component, so on a coordinate system where the unit vectors are E alpha. B, I could have written like the components in the coordinate system where the unit vectors are these. Well, they are essentially the same unit vectors. They are written in the same coordinate systems, but I just write sum over, the sum is over different, actually I can make it the same alpha. So this is alpha. And then you do A dot B. What do you get? You get these numbers A alpha, B alpha, and better I choose. Okay, so this is an important fact here, important combinatorics here, which I want to like to tell you right now. When I write A alpha, E alpha here, there is a summation, remember, which I am not writing. There is another summation over here. Now I could have written A alpha, B alpha, E alpha, E alpha in this line, which I was trying to write. But if I do that, then you may think, so let me write that and then I will change it. Why you should not write should be clear then. If I do this, remember that if alpha is repeated, it is summed over. So I may think that this means that alpha equals 0 to 3, A alpha, B alpha. There's the dot product between the two vectors, you should write the dot. So just like this. And then once I do that, so then you may try to break it out like A0, A0, E0 dot E0 plus A1, A1, E1 dot E1, etc. Okay, but this is not true. because what I meant is actually a sum over these two quantities and a separate sum over these two quantities. So I should not write both of them as the index alpha. The index which is summed over is often called dummy index. I should change that. So let me erase all these things which are not quite correct. I was just trying to show you how not to do the mistake. So let me go back, erase all these things and write the right thing. So this, if I want to write now, I should be careful because alpha is summed over. Here I should use a different index. And there is no harm if I use that index twice, once up, once down, then it is sum over is mentioned. And there's a dot between these. And from that we say that A alpha B beta, and then I get E alpha dot E beta. And now if you compare with this line, you realize that E alpha dot E beta is nothing but G. So this also we saw last time. And one more thing I would like to emphasize, this if I have to calculate the norm of a vector, which is essentially the length of a vector, so you can, so if A mod is the norm, then A mod square is nothing but the dot product of A with itself, which you can write as A alpha A beta G alpha beta. Okay, so these are the things mostly we learned last time. Let me remind you of one more thing, because we are talking about vectors here. Let me remind you of the idea of vector space. And I already assumed there that I need something for you to be aware of, which is called a field. I assume here that you already know what is a field. And I am writing this with a different color because this part is not directly related to our discussion, but still it will be good if you can have an idea about the vector space. Now, vector space we use at many places. One particular vector space you all should be very familiar with is the Hilbert space, which is the bread and butter of, which is the playground of quantum mechanics, so to say. So, what is the general definition of a vector space? It is defined over a field. So, let us call the field phi. Now, if you remember, field is a collection of objects, and let me just denote these collections as alpha, beta, gamma, so Greek letters essentially. This has nothing to do with the indices that you are talking about a little while ago. This is just, as you can see, the color is different. You are doing a little bit off topic, but will be important for us shortly. And quantities, these are the vectors. So this I called V, and again, so V, I can say denote as, so let me denote them as usual vectors, but this is true for any vector space, etc. And two operations. To define a field also you need two operations. So these two operations, one we will call addition and the other I will call multiplication. And with these are the backgrounds, these are the players, and there are certain axioms which a vector space should follow, and the axioms are the following. So let me, before I go to the axiom, I need to define what is the plus and multiplication. The plus and multiplication are between, so say if I have A plus B is what is this operation, and the multiplication is with a scalar. So this is the other operation. So what are the rules that it should follow? First is, I'm not going through them with utmost care because I believe that you already know what are these calls, etc., etc. So associative, additive identity, so additive inverse, sorry, minus u is the additive inverse of u, and then this is operations with the scalars. Okay, so these rules will be maintained. Then this V is a vector, and V is the collection of vectors, so it's vector space, and A, B, C, etc. are the vectors. Okay, so this is what we wanted to revise, and maybe some of this we will be using, but otherwise I just wanted to revise them. Now with this, let us come to our definition, first definition today, and that is we are trying to start with tensors. Now tensors also can be of different types, and we'll start with the simplest one. This tensors will denote with a bracket, a parenthesis with two numbers in it, and in this case, this is a tensor of this type. Now, sometimes this is called a tensor. I'm keeping it in quote. Covariant rank n. Now, the rank of the tensor and the covariant and contravariant, etc., is a little bit of old concept, but still, I will try to give you the dictionary between the old and the new, because sometimes you will read these things in the book and you should know what it corresponds to in our discussion. Now, a tensor is a device. You can think of it as a tool or a device which, if you put some input, it will give you some output. So, a tensor of type 0n is a device that takes, so it takes n vectors as input. What does it split out? What is the output? And gives does some operation with this n vector, gives out a scalar. Okay, so this is one criteria for it to be a tensor, that it has to take n vectors as input and give out one scalar if it is of the type 0n. And the other is that the output, the operations that it does, which gives you the output, is linear in the inputs. So there are n inputs. In the n inputs, the output is linear. Now, two vectors goes in, one scalar comes out. We have already seen such a thing, the dot product. So one example of a tensor will be something that takes two vectors in. So let's say these two vectors are A and B. So it takes these in. So these are like the tensor is like the function of these two and gives out a scalar. And when I say device, I mean roughly. So let me clarify what a device is. I mean roughly a function more precisely a mapping. Okay. So it takes two vectors, maps it to a scalar. And one such thing we have seen, the example of the dot product, is that I call this tensor G. It takes A and B and give you back A dot B, which is the dot product, which is a scalar. Okay. Now that is fine. That is the first criteria. Does it satisfy the second criteria? So what if we give in input the following thing? So G, let's say we give something like some alpha times A plus some beta. Alpha and beta are the fields, scalars times C. Now what will it? What will be the right hand side? Well, it will be the dot product of the first with the second. The first vector is, and the second vector is, and from the rules of the dot product, we know that this is equals alpha A dot C plus beta B dot C. And you see the way we have defined the tensor G. By the way, the tensor, a sign for tensor is this. Okay. So for a general tensor, we will use that sign. Now this I can write as alpha G taking A and C plus beta G taking B and C. You see what we have got? We have got this nice thing that G alpha A plus beta B comma C is actually linear in its arguments, and because of that you can directly do this. And this will be our friend. So it's linear in its argument. This will be our friend. That means that we will be able to use this to exploit many properties of the tensor. Now these should be true irrespective of any choice of the reference frame, because while writing this we have not evoked any reference frame at all. I have not written the components of A, B and C. So this are true irrespective of what reference frame it is. Let's take one more example. So how will a tensor of this type look like? Say n equals to 3. So it will have slots or places to put in 3 inputs, like if you wish A, B and C. So this is a tensor of, I should not put equals to sign here, but this is a tensor. So T is a tensor, which is the rule. Once I put in A, B and C inside, it again splits back a scalar. So remember, what is a tensor? Which part of this is a tensor? This T, which is the rule, the mapping. And the mapping is denoted by T. And it has 3 places in this case to put in inputs. That is the tensor. Once you do this mapping, then you get a scalar. And to do this mapping, you need to put in 3 vectors. Okay. Now, you see, G is a very special tensor. This gives you the dot product between A and B. If I use G on the same vector, it gives me the length of the vector, actually square of that. So this, let us measure the length of a vector. Because of this particular tensor is called metric tensor. Metric really means measurements. So let us measure one property of the vector, which is its length. And remember, that's a property of a vector that doesn't change. So remember, when I say metric tensor, G is a metric tensor. It's the rule G, which is the metric tensor. That is all right. But let's ask the question, how do I know that, so we have also come across about these quantities called G alpha beta. So what are they? Okay, so let us ask this question now. Now, to do that, we have to introduce the concept of components of the tensor. Okay, so let's first example. Let's say that I have a tensor T. Again, the same example, which is A, B, and C. This gives me scalar, right? But instead of operating it with 3 arbitrary vectors, I can operate it with 3 unit vectors also. So let us operate it with say E alpha is the alpha unit vector, and then here I put E beta, here I put E gamma. Okay. The question is, what is that I will get? I will get a scalar. That is obvious. This scalar I can level with alpha, beta, and gamma, because if I put another unit vector instead of the alpha, say let's take one example here. Say I would have put in alpha equals 0, beta equals 3, and gamma equals say 2. So in that case, I will get a scalar which I can label as T032. If I change what I put in as my vectors, I will get to label them as 1, 3, 2. Now, here how many choices do I have? For the first vector, I can, first unit vector, I could have put in either of 0, 1, 2, 3. So there are 4 of them, and then for each one of them, I have 4 choice for the second, and for each one of them, I have 4 choice for the third. So this 4 comes from the dimensionality of the space. So because I am doing in 4D space or space time, I get this 4, and the 3 is coming from the fact that it has a rank 3. So a tensor of, I'm using the word rank, or I can use like this, has scalars of number d to the power n, where d is the dimension of the space. Okay, so these are the scalars. Now the question is, what are these scalars? To understand that, let us try to use not unit vectors but any vectors as input to the tensor, to the rule that is called the tensor. How can I write this? Well, A alpha I can write in terms of the components and the unit vectors in one reference frame. Remember that all the vectors obviously I have to put in the same reference frame. I cannot just put in one reference frame and the other in other reference frame. That is kind of not nice. What is this? Well, you see that this should follow the linearity property, which means this A alpha, A beta, and A gamma are like our scalars or our fields when we discuss the vector space. So they will just get multiplied by and what I will be left with are the unit vectors inside the tensor operation or inside the operation that is called the tensor. And that we have already seen, that is what we called T alpha, beta, gamma, right? So this is what we will call the component of the tensor. This is essentially what we discussed here. There will be d to the power n of them. Now, this is all still kind of abstract. Let us jump into the most simplest case of a tensor, that is a vector, or that is not a vector. So we consider a tensor of type so if you wish you can call it rank 1, but I call it tensor of type. this type. This, because it's little bit more important than the higher rank or higher n tensors, this will have a special notation. The special notation for this will be like this. And remember that it will take one argument, one vector argument, because n equals to 1 in this case. Now this will call by another name, special name also. We'll call this a one form. Again, in old literature, this is also called but it is really not a vector. As we said that all objects, all tensors are like a rule. A vector is not a rule, it's an object. But this is a rule uh, which if you put one vector in it, it will give out a scalar. Okay. So this is, sometimes it is called a covariant vector or a covector. These are usually old notations, but anyway, we have just introduced it to you. What we will be most familiar with and comfortable with is a one form, calling it as a one form. Now let's see. So what is this, a one form? So again, let me write a one form here again. So it has all those linearity properties, and it takes a vector and then maps to a scalar. The one form is the device that maps the vector to the scalar. That is what a one form is, right? So if I again write it, so P takes a vector A, gives you a scalar. How do I write the components? Now we know how to get the components. Components are easy. You put in the E alpha unit vector, it will give you the alpha-th component. That alpha is written with a suffix here. So suffix. So which means if I now take the A vector in as the input and the A vector I write in terms of its components and the unit vector, you see what you get is A alpha P alpha, which looks like a dot product, but we are not still sure what it is. But this is a scalar that we know quite well. And the linearity properties holds. We have just used one of them, but just let me remind you. If I take things like this will give me alpha okay. Now, we have seen yesterday also the transformation properties. So let us come to the transformation properties of the vectors, unit vectors, and one forms. This is something which will be enormously interesting and useful for us. So let's come to transformation properties. Some we have already seen, so let me write those down in the left hand side. We have seen how the unit vector transforms. This transforms with a lambda, which is like this, and the components of the vector transforms the exact opposite way. The components of the vector has a inverse transformation property as that of the unit vector. This makes sense, and this is how we derived also, because if I have a vector A which is written in one coordinates like this and the other coordinates like this, if I transform one of them with one rule, the other has to transform with the inverse rule, because then only the transformation matrix multiplied with its inverse will give us unity. That is all right. So let me keep this part here. Let us look at how what happens to the covectors, or rather I should say one forms. So one form that we are talking about, we are writing it with P, and remember that if I put in the unit vector E in it, it gives me the corresponding scalar which is the component of it. So if I put in rather the unit vector as in the other reference system, then it's obvious that it will give me the component in that reference system. But this I can also write as E alpha prime. We know how to transfer, so I can write this as beta alpha prime E beta. These are numbers, they're not vectors. So again, using the linearity rule, they will just come out, and I will be left with so what is that? The right hand side is lambda beta alpha prime, and this is just the beta component, or yeah, the beta component of the one form. And in the left hand side, what do I have? The left hand side should be same as this. So this is this. So you realize that the transformation rule for the components of a one form is like this, which matches with the transformation rule of the unit vectors. Right? So what have we learned so far? So we have learned that, so let me write it here explicitly. This is something important. The components of the covector or contravariant vector or one form transfers the same way as the basis vectors or the unit vectors. On the other hand, this is the components of the covectors. The components of the vectors the vector that we started with. So this is the vector. This is the vector A. See, covector is just a rank 1 tensor, which is a rule. But that rule also I can put in different unit vectors into it, and it gives me different scalars, which I corresponding to the unit vectors, I can call it its components. Those things, those components transfer in a certain way when you change the coordinate system. It transfers just like the basis of the coordinate system transfers. You may ask the question, you should ask the question, that we call these as scalars. How is it that the scalars need to have a transformation rule? Well, if you look at here carefully, what I have written here and what I have written here are different things. In the top line, it is the scalar corresponds to the unit vector E beta. In the bottom line, it's the scalar corresponds to the unit vector E alpha prime. When I say unit vector, it is same as the basis vector. They're synonymous. So there are two different things, and we are asking the question: how is the transformation happens between these two things? They happens the exact same way the unit vector or the basis vectors themselves transfer. On the other hand, if I look at the components of the vectors like A, they transfer with the inverse matrix of the with the, of the of that of the basis vector, which we saw last time also. The components of the vector transforms with an inverse matrix with an inverse transformation. Rule compared to the basis vector. Now, because of this, these used to be called the covariant, and they used to be called vectors also, or covariant components. So let's say components. Co means same. So the same is emphasized by the co here. And in this case, because they are inverse, they're called contravariant. Contra means opposite. Okay. Now, what we call the contravariant components of a vector, we call those as our vectors. What we call vectors are essentially the contravariant components, or the components of our vectors are the contravariant components, and components of the one forms are the covariant components. So that is the mapping with the usual notation, old notation, with more modern differential geometry notation. If you look at this quantity, so let me write it as invariant. This is a very special invariant. If I have A alpha prime, P alpha prime. So what are these? Remember, A alpha prime is the alpha prime component of the vector A. P alpha prime. So let me remind you how we got A alpha prime. A alpha prime, E alpha prime is the vector A. And how you got P alpha prime? P alpha prime is the one from P, and you put in the alpha prime unit vector in it. Right? So this is how you got these two. Now these two, if I now try to write the transformation rules and write it in terms of the corresponding things in the unprimed coordinates, then I will alpha prime, I will get this. And for P alpha prime, it will transfer the other way. So I have to write here, say gamma. See, I do not choose beta because of the reason we just discussed a little while ago. But this index is alpha prime itself. And then I have P gamma. So this is A beta P gamma. But you remember that these two matrices are inverse to each other, and we have shown last time that this is essentially Kronecker delta. And once you do the sum over one of them, let's say sum over gamma, only gamma equals to beta survives. So this is A beta P beta. So see, this is form invariant. So let us introduce this terminology. That if I just change, if I keep the form same and change the coordinates, I get the exact same thing. That's why it's called form invariant. We have seen another example of this, which is G alpha beta, A alpha, A beta, which is same as that is also form invariant. In fact, wherever we will see that this type of operations will give a scalar, then it will be form invariant. Now, we introduced about the vector space, and I will request you to check the following statement. And this is important, that one forms satisfies to be members or to be vectors, or let me not say vectors, to be members in a vector space. It is the way we discussed or defined a vector space earlier. Okay, and it is this way a one form can be considered as a vector. It doesn't have the geometrical property of a vector, but this is the way you can consider this as a vector. What is the geometrical property of an one form? That we will discuss next time. Now, because I have this one form satisfies to be the members in a vector space, in a 4D vector space, so if I have a 4D vector space, I can always find 4 such vectors which gives 0 or doesn't give 0, which cannot be used to get 0 by linearly combining. Okay, what do I mean? So say I have these 4 of them. So remember that these are one form. So I write it this way. And because I have 4 of them, I level them this way. So these are 4 one forms. So I cannot find alpha, beta, gamma, and delta such that this linear combination is 0. So this is not possible. What basically what you are saying is the set is linearly independent. Okay, that's what I mean. So I can always find such things which are linearly independent if it's a vector space. These we will use to construct the basis one forms. We had the basis vectors earlier. This will give us the basis one form. What do I mean? I mean that now if I have this P, I can write this in terms of the components and the basis the same way as I was doing for a vector. So if I have P of the vector A, that then will be P alpha, because that's just a number. So P, I can write P alpha times the same rule with the unit vector now, unit basis, with the basis one form now. So this will just I'm sorry, so this is A, not E. This will operate on A. And if you go one step further, A I can write now in terms of its components and basis. A is a vector, and as you can see that this will come out A beta will come out. I get this basis 1 form with the unit vector E beta. The left hand side we have already seen is A alpha P alpha. When I do P on A, so this is, say, P alpha A alpha, doesn't matter which way you write, which is telling you that this has to be delta alpha beta. So you get the relation between the two basis of the one form and the basis of the vector, they are essentially delta alpha beta. Remember that this is not a number, this is a relation between two bases. There are four basis vectors in each side. So there is this relation between four basis vectors with other four basis vectors. So here you have 16 numbers. Often the following representation is used to denote the basis and all these components. So let me just digress a little bit and talk about representation. So vectors or basis vectors is written with a column matrix like this, and basis 1 forms then written with, this is, I'm just writing one of them with one of them. This is the thing. And then this operation essentially now means the matrix multiplication, and the matrix multiplication will be, I'm just not doing it for you here. It will be of this form. Have the column matrix following the row matrix. And if you know matrix multiplication, you will know that I will get, because this is 4 here, 1 here, 1 here, 4 here, I'll get a 4 by 4 matrix. And that in this case is nothing but the identity matrix, which has 16 numbers. All right. Now let's look at the transformation properties of the basis of the one form. Let me not derive it for you, you can derive it for yourself. The transformation property in this case is the following. And we should compare them with the transformation properties of the other things that we have seen. But let us come back to it in a while. So what is left to do today is to figure out what is the role of the metric tensor. And once I do that, we will just try to understand the different types of quantities that we have seen, and then we will call it a day. So what is the role of a metric? One role we have seen that it tells you the distance between 2 points. It essentially defines the dot product. Metric also maps a vector to a one form. Remember, a vector, let me again remind you, a vector is like A, which has components A alpha written in the basis of E. One form is a device, it's not a vector, it's a device where if you supply a vector, it gives you a scalar. If you supply the unit vector, then it gives you the component of the one form on that basis vector. And what was a metric? Metric, which is a second rank tensor, n equals to 2, which we should not say this tilde. This is a second rank tensor, and this requires two arguments, two vectors, because it's second rank. This was g alpha beta was its components, and then I can write it in terms of the components of the vectors and the metric. We have also seen that this, which is P on A, is also P alpha, A alpha. Okay, so this is the recap again. This is what we have seen so far. So let us construct now. Let's revise, which is G, the metric, and this metric I already have kept one place filled up. The other place is not there. What is this? This is a one form. Let us see why. Let us call this one form as B tilde. Then you see, if I take this will be equivalent to, one form has one place to put things in, this, which is B alpha, the alpha component of that. Is exactly what you expect if you would have gone from G. Because you see, if I would have gone from here directly, this is G, B I can write as that is B beta and this we have argued is G alpha beta. So what do we get? We get that B alpha is G alpha beta B beta. This is something, again, this is the relation between the components which will be extremely useful. So what we have done is that this is a way calculates components of one form from the components of the vector. By the way, it's not a one-to-one relation though. This is alpha and this index is beta. So to know one index, say alpha equals to 0, this beta is summed over. So you need to know all the components of the vector. Okay, so now we have seen that if I give you a vector b in a coordinate system, say S, I can associate few things with it. I can associate, given the coordinate system, the basis vectors. I can associate the components of the vector. I can associate the basis 1 forms, and I can associate the components of the 1 form. So for every vector, there is also a basis, there is also 1 form associated with it. Okay, so let us look at these and their transformation properties a little more detail. And that is where we will stop today. I am keeping the heading to be written later. Okay, so the left hand side will write vectors. On the right hand side, we will write 1 forms. Vectors say A, components of this in a basis is A alpha. Or basis, let me write basis. Right? Here, I have 1 forms. So the form you write like this. We are writing P, but you see that now we have understood for each vector there is a corresponding 1 form. So let us write it this way. These are the components and the basis 1 forms corresponding to it are these. The question is, how do they transform? How do they transform? So A alpha prime is when I'm writing this, I don't need to remember anything actually. What all I am doing is, I know that this index here is up. So I have to put that up index in the up of the lambda, and the bottom index of the lambda then has to be summed over with the up index of this A. It has to be summed over because once it is summed over, that index is not important. It is called dummy index. So the right hand side is also have an index minus alpha, index alpha prime. The left hand side is also same. The same way I can write the E alpha prime, etc. Now when I come in the right hand side, so I have A alpha prime. Now this will transfer like lambda beta here first and then alpha prime and then a beta, and I have the basis 1 forms. Okay. Now remember that 1 forms are the things that we introduced with the as a tensor, and it's a tensor which is important for us because if we write things in the language of tensors, then uh, things becomes form invariant eventually. Now I have here, you see that I have this basis vector transformation rule, and I have this one form transformation rule. They're similar, so these two are similar. That is why we call this a covector. On the other hand, if you look at these two now, they are similar. Their transformation rules, the transformation matrix, is exactly the same. And what are these? This is the unit or the basis 1 forms with the vector components. Okay. So it looks that there is a kind of duality between the description of a vector and the description of 1 forms. Why do I say so? If I start with a vector, I get the corresponding unit vector, the corresponding 1 form, and the basis 1 forms. But one can show that you can even start with this as the basis vector and this as the component of the vector. Then this will become the 1 forms and this will become the unit or basis 1 forms. So either side you can work with. Because of that, we call that there is a duality between the description of the 1 forms and the description of the vectors. Okay. We'll stop here. I'll just remind you that if I choose this as the basis, then in the old language, this is called the covariant components, which comes with suffix. And these are called the contravariant components, which comes with superfix or superscripts. Thank you.